So here we go again. Welcome back. I'm glad that you didn't get too bored last time and you found the energy to come back. You say, okay, you don't like philosophy. Let me just tell something about what we discussed last time, just 5 minutes to recap. Everything started from a personal point of view. If you remember, this first slide was a paraphrase of a well-known statement done by a famous Prussian general, von Clausewitz, who said that war is the continuation of politics, remember? And so I just liberally adapted this sentence to reflect my personal view, which is basically, for me, machine learning is just a continuation of epistemology by other means. In the sense that, as I explained last time, for me, for machine learning researchers, we are basically trying to solve the same problem. We are trying to address the same questions that philosophers have raised a few centuries ago, actually, but we are doing this with other means, using algorithms, using computational methods, and so on and so forth. So I think in general it's a good idea to have a big picture of what we do in machine learning by considering the philosophical background of our own discipline. So last time we spent, of course I'm going to skip all these slides. Last time we spent a lot of time discussing about induction, the so-called problem of induction, which for philosophers have been a problem for a while, and we explained why. And both from a logical point of view, if you remember, there are some logical paradoxes behind induction, and we try to address all these issues. But at some point, we also discussed the fact that some people in philosophy think that induction, there is more to machine learning or to inference than simply induction. And at the end of the talk last time, I just described one of probably the most famous attacker to the induction process, which was Karl Popper. Karl Popper basically said that there is no induction, and so we discussed these things last time. Now, it's a no chance that we devoted the entire talk last time talking about induction, because induction is probably one of the most problem in epistemology. And of course, it's the main problem in machine learning. So today I'm going to touch briefly upon 3 other subjects, which is the role of intuition versus the role of induction. And then I will be talking about the quest for interpretability, or the quest for explanation, which is a favorite word for philosophers. And then at the end of the talk, I will be briefly talking about the quest for scientificity. So I'm going to skip all the slides that I used last time. I will just go to the right one. I think it's this one. Here you go. So induction versus intuition. We already started thinking about this last time. So last time we spent a lot of time discussing what philosophers think about scientific discovery, right? We talked about Popper and other philosophers. One might argue that these thinkers are kind of, how can I say, armchair thinkers. I mean, philosophers do not do science. And so a scientist could say, well, you are not really a scientist. Why do you pretend to tell me how to do my own work, right? So I think it's a good idea to see what scientists actually thought about induction. And so let me start by quoting some well-known and famous scientists. Actually, there are 3, all of whom got a Nobel Prize, so they are entitled to be considered great scientists. And let's start with Steven Weinberg. He's a physicist. He got a Nobel Prize in physics, I don't remember when, in the 70s, I think. So Weinberg says, well, scientists and historians of science have long ago given up the old view of Francis Bacon. Remember, Francis Bacon was the champion of induction. He was the one who said we should get rid of deduction in the process of discovering the truth, and we should use induction. So he says, scientists and historians of science have long ago given up the old view of Francis Bacon that scientific hypotheses should be developed by patient and unprejudiced observation of nature. It is glaringly obvious that Einstein did not develop general relativity by poring over astronomical data. And this is one view. He says that basically a working scientist doesn't use induction when he solves his problems in physics in this case. Well, he mentioned Einstein. Let's see what Einstein said about induction. And he also had a very clear idea. The truly great advances in our understanding of nature originated in a manner almost diametrically opposed to induction. So he's another opposer. He didn't like the idea that we do science by simply looking at data and just somehow finding out some structure or some truth. Let's consider our third scientist, again a Nobel Prize winner, but this time in medicine. He was very famous. He was a biologist, Peter Medawar. And he is interesting because he speaks about the theatrical illusion of science. So he basically says, deductivism in mathematical literature. In mathematics, you have the so-called deductive method. You start from axioms and then you derive the truth by a rule of inference. And inductivism in scientific papers are simply the postures we choose to be seen in when the curtain goes up and the public sees us. So it's a kind of justification a posteriori. It has nothing to do with the psychological processes behind scientific discovery. So he makes an important distinction, which is a very famous distinction indeed in the philosophy of science, between the process of discovery, the so-called context of discovery, and the context of justification. So he said one thing is the mental process according to which I discover a new theorem or I discover a new fact in physics and stuff like that. Another story is how I justify my finding to my colleague, with respect to my community. And so I use deduction, for example, or induction. So, three well-known working scientists didn't believe in the power of induction in discovering truth and in finding scientific inferences. Actually, the list is very long. I just limited the number of scientists who don't believe in induction just to three, but it's a very spread idea that in reality, working scientists do not really follow an inductive process. This is another quotation. Alfred Whitehead used to be a mathematician, and then he turned to philosophy. And this is another, opposer, if you like, opponent of the induction process. He says, induction has proved to be a somewhat more complex process than Bacon anticipated. And we know that this is a very inadequate account of the processes which issue in scientific generalization. So, if induction, according to these scientists, is not the right process behind scientific discovery, what is the truth? What's going on in the scientist's mind when he discovers a law, a theorem, or whatever? Well, the answer is intuition, and that's the thing I want to stress right now. And let me mention another philosopher, Mario Bunge, who basically says something which I agree with. He says induction is certainly powerless without the invention of audacious transcendent hypotheses, which could not possibly be suggested by the mere examination of experiential data. So even if I have a bunch of data, million observations, I need something else. And this is intuition, right? The power of intuition. We have to have a perspective, and somehow the human mind finds a structure in this data. I would like to be clearer about this, and because I think it's important to show you some example of real intuition. I don't know whether you know this gentleman here. Some of you, I'm sure you know. His name is Andrew Weil. By the way, he just got the so-called Nobel Prize in mathematics, the Abel Prize, and he became very famous because after centuries, he was able to prove the well-known Fermat's last theorem. Probably many of you know the story behind this. Pierre de Fermat once wrote in a book of his in a margin of the book that he had found, here you go, I've discovered a truly marvelous proof of this, which this margin is too narrow to contain. And this was this theorem. Basically, it says that it is not possible to find three integers, x, y, and z, integers, such that x to the power of n plus y to the power of n is equal to z to the power of n if n is greater than or equal to 3, right? When n is equal to 2, you get the classical Pythagorean theorem, and then, of course, there are integers. For example, 3, 4, and 5 will do. But if n is greater than 3, so you can consider this as a generalization of Pythagorean theorem, there is no integer solution for this equation, right? So Fermat wrote this small sentence as a margin, in a margin of his book. So everyone believed that the proof was very simple, and indeed it took a few centuries for mathematicians to come up with a proof of this theorem. And the proof was found by Andrew Wiles. It was a very complicated proof, actually. He used very sophisticated method in mathematics. So it's still a mystery of how was it possible that Fermat, with the tools available at the time, was able to prove this theorem. Now, I have a video for you. Some of you already have seen this video, because I talked about these things at the Christmas lecture.
Just one question.
Yeah.
Is there any proof that Fermat actually proved this, or is it just making some record?
This is a recursive notion. No, what we had is that this margin over there, so there is no proof that he actually proved. Maybe he just had some intuition, but there is no proof that he proved that. Okay, let's watch this video. I hope the audio worked. Where is Felix? Here we go. Okay. This is an interview done to Andrew Wiles, I think a few years ago.
Perhaps I could best describe my experience of doing mathematics in terms of entering a dark mansion. Goes into the first room, and it's dark, completely dark, and stumbles around, bumping into the furniture. And gradually you learn where each piece of furniture is. And finally, after 6 months or so, you find the light switch, you turn it on, suddenly it's all illuminated. You can see exactly where you are.
Nice desk, right? It's worse than mine.
This desk, when suddenly, totally unexpectedly, I had this incredible revelation. It was the most important moment of my working life. Nothing I ever do again will.
So you see, it was quite moving just to remember how we got to that idea. But you know, this is exactly what I wanted to talk about, which is this very moment, the so-called eureka experience, the haha experience, when you are working on something. Maybe you are not proving a theorem, maybe you are solving a simple problem, and so suddenly the solution comes up to your mind. And this is basically the power of intuition. Now, let me tell you a short story, which goes back to the beginning of the past century. And we have another great mathematician whose name is Henri Poincaré. He was one of the greatest mathematicians and physicists of the 20th century. And he also anticipated, to some extent, the theory of relativity that then was proved by Einstein. And at some point in his career, he felt obliged to write a very short paper where he described the psychological processes behind one of the most celebrated mathematical theorem that he proved. So he published this very short paper in this book called Science and Method. The third chapter, actually it was a presentation at a conference, then he collected the paper in this book. The title of this small chapter is Mathematical Discovery. And so basically, this is probably the first time that a mathematician tells the story behind the discovery of the proof of a theorem. Not just the proof of the theorem itself, but the psychological processes behind this. So let me just quote from one part of this paper. So basically, the story is simply this. He was working hard to prove a theorem, a very important one, actually. But he was just failing. He was not able to prove the theorem. So maybe he was working for 2 weeks or so without any success. And then after working so much on this problem, he made a trip with some friends. And this is the point I want to make, he says, just as I put my foot on the step, the idea came to me, though nothing in my former thoughts seemed to have prepared me for it, that the transformation I had used to define Fuchsian function, which is this function he was working on, were identical with those of non-Euclidean geometry. Basically, at that very moment, he saw the proof of this theorem he was trying to find, right? So again, he had this moment where somehow he had a vision of what was going on. Now, this small paper by Poincaré was very influential because, as I mentioned before, probably was the first time that a well-known mathematician wrote about his psychological or mental processes. And so another mathematician, a very well-known one actually, Jacques Hadamard, was very inspired by this paper and tried to understand what's going on in the mathematician's mind when he tries to prove a theorem. And for example, he interviewed great scientists. He interviewed Einstein, for example, to see what's happened in a scientist's head. And he wrote this very nice book, The Mathematician's Mind, where he put forward a theory of mathematical discovery, I would say in general of discovery. The theory is basically this, and in Graham Wallace we also find a precursor of this. So there are basically, according to this theory, 4 steps which are typically involved in, proving a theorem or in solving a problem. You can see the process of proving a theorem as a problem-solving activity. First of all, there is the phase, so-called preparation phase, where you are working hard trying to solve your problem, maybe proving your theorem or stuff like that, and you fail because the problem is too complex. Then you do something else. You take a shower, you go outside, you have breakfast, you have lunch, whatever. But, and that's the main point of the theory, somehow in our subconscious part of our soul, we are still working on it, although we are not aware. So our brain is still working on this. And then suddenly we have the eureka effect. We have this illumination. Suddenly we see the solution of the problem, if we are lucky, of course. And then there is a 4th step, which is a mere technical step to verify mathematically that, or formally, that our intuition was correct. In this illumination phase, we are kind of aware that the problem has been solved. So somehow you know, you see, you feel that you have solved this problem. Now, this reminds me of a very interesting theory which has nothing to do with cognition, because now we are talking about cognition. And the theory goes back to a very well-known school of psychology called Gestalt Psychology, which mainly devoted, they were interested mainly in visual perception, in perception in general. They introduced this notion of Gestalt, which literally, let me just mention, it's not clear what a Gestalt is, but I will show with an example what they have in mind. For example, let's quote from this very well-known book, Gestalt Psychology. Köhler says, in most visual fields, the contents of particular areas belong together somehow, as circumscribed units from which their surroundings are excluded. Or, another definition, in Gestalt theory, the word Gestalt means any segregated whole. Now, this is an example of a Gestalt, a visual example. If you look at these visual stimulus, I'm pretty sure everyone in this room, if I ask you to describe this stimulus, we say, I see a circle surrounded by some clutter. This is the verbal explanation that I'm sure all of us will give. So somehow we are considering this stimulus as something unrelated from the background. We are taking something, but taking some structure from the data. Well, this is a Gestalt, technically speaking. So what has this to do with this notion of you know, the haha experience, the eureka experience that I was mentioned before? Well, because some scientists think that this Gestalt process works not only in perception, in visual perception, but also at higher levels of cognition, right? And this is, for example, the position of Michael Polanyi, a chemical physicist who then turned to philosophy, or Konrad Lorenz, who went so far as to say that every discovery of a complex regularity comes into being through the function of Gestalt perception. So we are not talking just about perception, but we are talking about high cognitive faculties. Now, let's consider this example, this haha experience using some visual phenomena. For example, if we look at this cube, well, a cube, we interpret it as a cube. If you look at this stimulus, and if you keep looking at this, at some point, I'm pretty sure you will see another thing. There is a so-called Gestalt switch. So maybe for some time, you see this cube as a three-dimensional cube, where maybe this phase is the closest to you. And then suddenly, if you keep looking at the stimulus, suddenly there is a reversal. And you will see that this cube, or this phase of the cube is closer to you. So this very moment, when you change perspective, when you see something else, might be related to the aha experience that I mentioned before. There are several examples. This is another famous one. If you keep looking at this picture, you might see, depending on your starting point, you might see an old woman, for example. I don't know, this is the nose of the old woman, and this is the hair and stuff like that. Or suddenly you can see a young woman, right? This is the ear of the young woman. And again, this change of perspective, this change of interpretation is sudden. It's not a gradual process. Another example, you can see a rabbit or a duck, and again, when you change perspective, this change is very sudden. So, you know, there are some people who think that these phenomena are not just confined to visual perception, but also to cognition. So intuition apparently plays a very important role, according to many important scientists. But can we define intuition? Well, this is tricky, because following Mario Bunge, but also other philosophers, intuition refers to all the intellectual mechanisms which do not know how to analyze, or even name with precision. And so it's something which is cannot be captured by a definition, an algorithm, or stuff like that. And so here we have two different, how can I say, perspective about intuition. So there are those, like, for example, our friend here, Mario Bunge, who says that intuition cannot be captured by an algorithm or by formal analysis. And this is confirmed, for example, by Hans Reichenbach, a philosopher of science, who says that the act of discovery escapes logical analysis. It's something that we cannot analyze logically. There are no logical rules, or if you like, algorithms, such that we can build a discovery machine. On the other hand, we have people like Herbert Simon. Herbert Simon has been a Nobel Prize in economics, and then he turned to artificial intelligence, and he was one of the founders of artificial intelligence. He was very interested in the notion of intuition and cognition. Well, we have the opposite perspective. According to Simon, intuition is very simple to understand. It's just matching. For those of us here who do pattern recognition and machine learning, we can say pattern matching or graph matching, right? The situation has provided a cue. The cue has given the expert access to information stored in memory. So we have memory, a lot of cases. Then I have a new case. I match the new case against the existing ones in my memory, and in the very moment I find a good match, this is intuition. Well, you know, I don't have a crisp answer. I don't know whether he's right or he's right. But just as usual, I want to give you the idea that these problems you're talking about are very difficult, and there is a long-standing debate behind this. Okay, if you're interested in these things, which are very interesting indeed, of course I suggest you Hadamard's book, The Mathematician's Mind. I suggest you also to have a look at these enjoyable books. Polya, those two books have been written by Polya. This is more accessible, maybe, how to solve it, and it provides a very interesting perspective to mathematics. Usually we are taught mathematics in a deductive way. These are the axioms, this is the proof, this is the theorem, this is the corollary, and so on and so forth. Here and here as well, Polya is interested not in the proof itself, but in the psychological processes. For example, he plays, according to him, and I agree with him, he plays a lot of emphasis on the role of analogy when we discover a truth or we prove a theorem and stuff like that. So indeed, the title of this, the subtitle of this book is Induction and Analogy in Mathematics. This is more technical, but this is very enjoyable. So if you have a chance, have a look at it. Okay, now let's change topic. Let's talk about the quest for interpretability, which in philosophy of science has another name. It's called explanation, the notion of explaining a model. Let me start from a very recent paper by Rich Caruana, a very well-known machine learning researcher, who recently, just a few months ago, at a workshop of human interpretability in machine learning, gave an invited talk whose title I like a lot, Friends, Don't Let Friends Deploy Models That Don't Understand. And basically, he makes a distinction, which is quite obvious, but it's important to stress this point, between the accuracy of a model, on the one hand, and the interpretation of this model, the interpretability. And unfortunately, it turns out that there is a trade-off between these two things. It turns out that the most accurate models usually are not very intelligible. These are, for example, neural networks, deep networks, I'll be talking about this later, random forests, boosted trees. They are probably the most powerful machine learning algorithms around, but they are not intelligible. If you ask an explanation or an interpretation of this model, it's difficult. On the other end, the most intelligible models, for example, linear regression, logistic regression, which are very simple to interpret, they are not as accurate as the other ones. So it looks like there is a trade-off between interpretability on the one hand and accuracy on the other end. For example, let's take the most popular machine learning model around these days, deep neural networks. Some of you are quite happy, I'm pretty sure about this, especially that area over there. So if you are not familiar with deep neural networks, this is basically a neural network with many, many layers, maybe tens, 50 layers. I've seen a deep network with some 60 layers, some point, even more. So what happens? Input from the external world is fed to the network in the input layer, and then it's propagated in some way, layer after layer, until it reaches the final layer, and then the network provides some answer. Now, what happens in between? Here you have a lot of parameters, weights, they are called the weights of the network, millions of parameters, and the learning process, the training process, consists basically in finding these parameters in such a way that the network is able to perform the desired input-output behavior. And now, what happens if I ask you to interpret this model? Can you interpret it? So you can say, well, I know why the response is blue, because in neuron 375, the weight is 0.06, it should be 0.07. It's crazy, right? So it's not possible to interpret these models in an intelligible way. Well, there are other one could say, okay, why should we stick to neural networks? The classical answer is because they work very well. Actually, they are the best models around. But there are also other models which are very good, but not that good. And in any case are more intelligible. For example, decision trees. Decision trees are a very simple structure. It's a tree where at each node you have a question, maybe a binary question. Is sex male? Yes or no. If yes, you go there and you ask another question. Is age greater than 9.5? And so on and so forth. Until once you ask the right questions, you get with some decision. I don't know, here, died, survived, or whatever. I took it from the internet. I cannot be blamed for this. Okay, so for sure this is more intelligible than a deep neural network with millions of parameters. But in real-world applications, you don't have these small decision trees. Maybe you have something like this, with hundreds of intermediate nodes, with hundreds of intermediate questions. So the question is this intelligible or not? Well, for sure it's more intelligible than a deep neural network, but still is not that intelligible as we might imagine. Now, interestingly enough, this notion of intelligibility or interpretability or comprehensibility, sometimes it's called, is an old question, is nothing new under the sun. This is a very famous paper in the 80s, so we are in 1983, by Richard Michalski, one of the father of machine learning from the symbolic side. He wrote this influential paper, a theory and methodology of inductive learning, and here he put forward what is typically known as the comprehensibility postulate, which is basically this one. He says the result of computer induction, if you like machine learning, should be symbolic description of given entities, semantically and structurally similar to those a human expert might produce observing the same entities. And this is the important point. Components of this description should be directly interpretable in natural language. So according to his postulate, comprehensibility postulate, any machine learning algorithm should give me the answer, but also an explanation in natural language as to why the model produced that response. Now, he wrote this in the 80s. Of course, nowadays, it's just crazy to think that we have something like this available, but some people are working on this. So after many, many years, there is a research group led by Zubin Garamani, a very well-known machine learning researcher, professor at Cambridge, who just started, just a few months ago actually, a project which is called the automatic statistician. So this, according to the claims done by Garamani and his group, the goal of this project is to devise an algorithm, a machine learning algorithm, which not only provides some answer concerning a problem or whatever, but also provides a report as to why the answer is that or this. So this is just started, so I don't know whether it will be a success or not, but it's a very challenging problem, of course. But, and this is the point now I want to make, some people in the machine learning community say, but why should we care? Why? For example, let me take two representatives of this camp, those who say, why should we care? So, for example, let's take Stéphane Mallat, a very well-known French machine learning researcher. He says something which is quite deep, which has to do with a notion which was put forward many years ago. Sometimes this is called the tacit dimension. Tacit dimension means that when you do science, maybe with this quest for objectivity, at some point it enters somehow some tacit knowledge that you use, maybe in your experiment, on your model and stuff like that. So the quest for objectivity, pure objectivity, is simple and ideal, which is not encountered in practice. So for example, he doesn't mention this tacit knowledge, this skill that you have. For example, if you ask a pianist why he plays the piece that way, maybe he can't tell you exactly, because maybe it's too fast and he's not able to provide you with a description why he's doing that. Now, he says there are things we cannot verbalize. That's the main point. I cannot say in natural language why I do this and why I do that. For example, he says when you ask a medical doctor why he diagnosed this or that, he's going to give you some reasons, but how come it takes 20 years to make a good doctor I mean, if everything is written in books, so expressed in natural language, why it takes 20 years to have a good doctor? There must be something else. Maybe the skill that he has acquired by experience, this tacit knowledge that he has acquired. This is interesting, this other position. So very crudely, he says, well, why should I care? You use your brain all the time. And you trust your brain all the time. And you have no idea how your brain works. So why should we care why a neural network works and stuff like that? Well, this is true to some extent, but I mean, recently this problem has become very important in machine learning, because nowadays machine learning is also being applied to things where you might have legal actions. For example, you go to your bank and you ask for a loan, and then the decision comes out, but the decision is actually a decision taken by an algorithm, maybe a machine learning algorithm. And the decision is no, I don't give you this loan. Now, legally, the bank has to tell the customer the reason why the loan has been denied. And of course, if you treat your machine learning model as a black box, you can't say, well, the black box told me so, and that's it. So there are legal domains where you are required legally to provide an answer. And nowadays, machine learning is becoming very popular in this area. But now let me go back to the philosophy of science and stuff like that, because all this discussion that today we have within the machine learning community about the comprehensibility or the interpretability, indeed it's an old story. And in particular, I like this quote by Peter Abelard, who became famous probably for the most famous love story in the history of humankind. You know the story behind Abelard and Heloise. Heloise was his pupil, and they got in love, and then they got prisoned, and there was this love letters from Abelard to Heloise. It became a classic in the history of philosophy. By the way, he was a philosopher. We're not talking about his love affairs. And we are in the Middle Ages, actually. And he wrote this interesting thing, which we can use today by just changing maybe medicine, here you go, with deep neural network. You change medicine, put deep neural network, you get a sentence which might be uttered today. Many people are practicing action but have little scientific understanding. They have tested the healing power of deep neural networks and are good at healing because of their experience alone, but they do not know much about the natural causes. That's interesting, because it says that you cannot, if you have some skill, or if you have a scientific model in general, this scientific model should provide you an explanation, right? I like also the second part, because basically he likens those who don't understand the causes to beasts. So he says, beasts and all other irrational animals are very sound in practice, but are ignorant of natures and causes. And finally, the man of understanding is he who has the ability to grasp and ponder the hidden causes of things. Now, this boils down to a very serious issue in philosophy of science, the distinction between explanation on the one hand and prediction on the other hand, which goes back to Aristotle, probably even earlier. One thing is to predict why something happens, and one thing is to say how it happens. Let's take one example. I don't know, Newton's law of gravitation, right? There is a nice formula. Everyone has learned the formula at high school. Two bodies attract each other according to the inverse of the square of the distance, blah, blah, blah. That's explained how, right? It doesn't say why, and that's the main point. It doesn't say why these two bodies attract each other. It's a mathematical description, and it's a knowledge how rather than a knowledge that. And indeed, you know, notice the time frame. Here we are in the Middle Ages under the influence of Aristotle, and now we are with Galileo at the beginning of the scientific revolution, and his view was totally different. And he made it very clear in his writings. He says, let me read, "The present does not seem to me to be an opportune time to enter into the investigation of the cause of the acceleration of natural motion. concerning which various philosophers have produced various opinions. Such fantasies, and others like them would have to be examined and resolved with little gain. So basically he says, we don't care about causes, we don't care about explanation. If I give you the right formula which predicts where the falling body will arrive after, I don't know, throwing it away, why should I ask why? A similar view was taken by another giant in the history of science, by Newton, who very famously put forward the same idea. And the reason is simple. This is a scholium in the Principia, a marginal note. So he says, I have not as yet been able to discover the reason for these properties, or for gravity from phenomena, and I do not feign hypothesis. Why? Because I don't want to use, and that's the main reason, occult qualities. So if I have to explain to you why two bodies attract each other, I have to make recourse to some metaphysical notion. For example, some people use this notion of action at a distance. But action at a distance is a kind of metaphysical notion. I cannot observe it. And according to modern philosophy, which was created by Newton, Galileo, etc., we have to get rid of all these metaphysical or occult qualities. So the motto for, after many, many years, we are now in 1966, the motto for a while in physics, in many hard sciences, was ask how, not why. By asking how, this is the same position as Steve Malat for deep learning or Pierre Baldi. Don't ask why it works. It works, that's it. That's the reason why I take this model and not that one. And you know, eminent scientists such as Kirchhoff, Ernst Mach, all within the empiricist school, they exactly postulated not to ask the reason or an explanation of natural phenomena, but just ask for mathematical formulas and ask how it was in one sense forbidden in science for a while. And now we are in the realm of statistics. And Carl Persson, who was one of the founders of modern statistics, was very well aligned with this approach. For example, he says we should get rid of all these metaphysical or occult qualities. Matter, force, for him, were just metaphysical or fetish. We should get rid of this. And another thing we should get rid of this is the category of cause and effect. Modern empiricism just didn't like the notion of causality, for the simple reason that there is no way to see whether two things are actually one the cause or the other. What you can actually see is a correlation. You just see that phenomenon A happens very often together with phenomenon B. But you don't know whether A is the cause of B or B is the cause of A, because there must be some other phenomenon maybe which provokes both. So it's the main point made by Persson and all those philosophers, or statisticians in this case, who just got rid of the notion of causation, was that we can only observe correlation, and correlation is the real thing. And indeed, if we open every textbook in statistics, you will find this idea that statistics is all about correlation and no causation. Now, the question is, are those days over? One might get the impression, the wrong impression indeed, that statisticians no longer are interested in cause and effect. And here there are a few statisticians, I'm not sure whether you will agree with Rubin or not. I think he's a professor at Harvard, I think, right? So, yeah. So he says, fortunately, the days of statistics can only tell us about association, and association is not causation, seems to be permanently over. So again, a heated debate within statistics concerning the notion of causality. Let's go back to big data or machine learning or whatever, because the philosophy behind machine learning and big data is exactly the one put forward by the empiricists that we saw before. When you have a lot of data, you cannot discern causality. You can only learn about correlation. And correlation is the real thing. So again, 2013, in this very well-known textbook on big data, they say The idea of identifying causal mechanisms is self-congratulatory illusion. Big data overturns this. Again, back to Pearson, that correlation is the real thing. So Pearson is back, works at Google, because this is an interesting quote from this paper, which I already mentioned last time, The End of Theory. According to the author of this paper, the availability of huge amount of data is basically the beginning of the end of the scientific method as we know it, which consists of finding a model and applying the model to data. Data is the real oil. So again, correlation supersedes causation, and interesting enough, it's time to ask, what can science learn from Google other than the other way around, right? Very bold statements. Now, in the machine learning community, however, there are people, actually very well-known people, who work on causality. There are some philosophers like Glymer, Shines, Sturz. There's Julia Perl, who invented Bayesian networks, basically. We're trying to see whether by looking at data, we can infer causal phenomena. So they believe in the fact that we can. They simply claim that probability theory and statistics alone is not enough to do this, and I think they are right. And they basically try to use tools from graph theory, graphical models, and statistics to try and understand whether we can infer causality from data. To tell the truth, this area in machine learning has been active for quite a few years. It has never taken off like deep learning, for example. There are still a lot of people working on this, but the results that they got so far are not so exciting. Okay, so let me conclude with the final part, the quest for scientificity. And let's go back to the 90s in computer vision and machine learning. At some point around the 90s, a lot of people started urging the community to make the discipline of machine learning and computer vision, which are very related, more scientific, whatever it means. The idea was that machine learning is a science and should be an experimental science. And since this is a science, it should rely on observation and data and on actual measurements. Now, this nowadays seems obvious because all machine learning is dominated by data-driven technologies, but at that time was not that obvious. So talking about computer vision, they said computer vision research then companies had a boom period in the first half of the 80s, but now things, we are in the 90s, are not that rosy. So we believe that computer vision can be turned around from a field in shambles to a respectable and balanced science. The point was we should use more experiments. More or less the same thing, we are more or less in the same years, happened within the field of machine learning. Nowadays, the two fields are very much related. There is a big overlap between the two, but at that time, there were kind of two separate fields. So Pat Langley was the founding editor of a prestigious journal called Machine Learning. In the editorial of the first issue of the journal, he wrote this paper, Machine Learning is an Experimental Science. And again, the same thing. Machine learning is a scientific discipline, and so it has both theoretical and empirical aspects. And so in order for machine learning to make scientific progress, and in both papers there was a lot of emphasis on progress, on scientific progress, we encourage researchers to join this evolution by making the field more experimental. Now, first of all, let me say something about this notion of scientific progress, because there is a very naive view according to which science proceeds in an incremental way. It's a progressive endeavor. So basically, every time a scientist writes a paper or finds some scientific finding or whatever, it basically adds a new brick to this building which is growing towards the truth, whatever it is. Okay? Now, this is a very spread belief. Actually, even professionals George Sarton was the father of the history of science as a discipline. And in the 30s, he wrote exactly this. He went even farther by saying that the notion of progress has no definite meaning in other fields than in science. Now, this notion has been questioned very much by Thomas Kuhn. Probably you are familiar with this, because Thomas Kuhn just shattered this simplistic view of science, which basically says that science is an incremental process, and step by step, sometimes we reach the truth. And that's the book which was the beginning of a new approach to the notion of progress, the structure of scientific revolutions. The basic idea behind this book can be summarized very crudely in this nice sentence. Basically, the idea is the following. When you have a scientific field, there are some stages, some phases. At the very beginning, there is a kind of pre-scientific era where every scientist tries to provide his or her solution to the problem, and there is no unifying concept, there is no unifying approach. It's a kind of chaos, right? Then at some point, a new result is discovered, and maybe a new fact is discovered, or a new model, and then everyone is excited about this result because it explains a lot of things, and in the community, everyone gets convinced and works within that particular model. And so we have this notion of normal science. So basically, the vast majority of the community works in that particular field. This happened, for example, in science after the revolution done by Copernicus, not immediately though, happened after Newton, after Galileo, after Einstein, after Darwin, right? Then we have a model, everyone works within this model, but from time to time, some anomalies are discovered. There are some facts in the external world which do not quite fit the model. And so these anomalies keep accumulated, and then at some point, there is a crisis. There is a crisis, and when we have a crisis, then we have a revolution. A revolution means that some new paradigm, some new model, some new theory is put forward. And sometimes this new theory is totally in contrast with the old one. Think of the Copernican view of the world, and think of what people think before that. So everyone gets convinced that this is a new model working on, and then we start again normal science, everyone works there, there is incremental improvement, and then again crisis, and so on and so forth. So instead of having a straight line, so progress is not a straight line, it's like a spiral in some sense. So the key notion behind this model is the notion of a paradigm shift. Now, I could spend the whole lecture talking about the notion of a paradigm shift, but since one picture is worth 1,000, we are in the big data here, 1 million words, 1 billion words. Let me just show a single picture. This is the notion of a paradigm shift. This is how high jumpers used to jump before 1968, okay? And then we had Dick Fosbury in Mexico City in 1968. We jumped in a totally different way. That's a paradigm shift. That's it. I don't have to add anything. At some point, all people in the field were convinced that this new paradigm was more successful than the other one, and everyone now jumps this way. It no longer jumps that way. So this is a notion of a paradigm. Now translate this into science or into mathematics, and you will get the notion of a paradigm shift. Okay, so much for the notion of progress, because as you've seen in all these papers, we keep talking about progress of science, progress of machine learning, and so on and so forth, but let's consider that this notion of a progress is not that obvious. Now, another important myth, another important aspect of science, which characterizes actually the scientific method, is the notion of measurement, right? This is so important that some scientists like Thomson, Kelvin, said if you cannot measure it, it's not scientific. When you cannot measure it, when you cannot express it in numbers, your knowledge is of meager and satisfactory kind, which is more or less what Galileo said when nature is written in this book, written with mathematical formula. Now, this is another thing we should consider. in order for a science to be considered scientific in some sense, according to those working in the hard sciences, we should be able to measure our notions, our concepts. And indeed, this is what people have done in machine learning. So people started collecting data sets in order to measure, first of all, to train the models, but also to measure the performance of the models. And so we started, probably you are too young, or maybe you are outside the field. I remember when I started my career, and if you develop the an image processing algorithm, you have to test your algorithm over these two images, Lina and Cameraman. By the way, Lina was, I don't have to tell you, but it was the cover of a Playboy issue. Sorry about that, but that's the truth. And that's Cameraman, right? So you develop your edge detection algorithm, you have to try on this image and on this image. You got some results and you published your paper. The same thing happened in machine learning. You develop your model and you have to test on very toy example like this one. This was an example invented by Michalski. You have some trains going eastward, some trains going westward. You have some features which characterizes the couches, and then you have to learn whether your train will go eastward or westward. That's the test. If your algorithm succeeds in solving that problem, you had a paper, right? That was basically what happened in the 80s and in the 90s. And nowadays, we have moved to the age of data sets. People started collecting data sets for all possible problems. This is an example of ImageNet, probably the largest database of images for image classification. The machine learning community has developed hundreds of data sets on all possible problems around. So you can test your algorithms over these data. So what's next? Well, let me say something about data sets. Of course, there is no question here. The use of data sets was very beneficial for the community. So if today we have machines in my phone, I can find a face with my camera, a face detector, speech recognition system, OCR system. If we arrived at this, it's because of the availability of all these data sets. But we should be careful a little bit when we consider the power of data sets. For example, let me mention this study here, which was quite important just a few years ago, 2011, published in the Computer Vision and Pattern Recognition Conference. They asked this question. Basically, they wanted to address this issue of bias in data sets. So they asked, what is the value of current data sets when used to train algorithms for object recognition that will be deployed in the real world? That's the problem, not just in your laboratory. This is the answer. The answer that emerges can be summarized as better than nothing, but not by much. So despite the success that we had in machine learning thanks to the availability of data sets are still a problematic notion. Why? Because of the presence of bias. And I'm going very quickly to explain what I mean with this. So, this is an example of what they did. On the one hand, we have the real world with billions and billions of cars. For example, let's consider the problem of given an image, tell me whether there is a car in the image, a problem that we can solve in milliseconds. So what people did in the past few years was to collect very large data sets of cars. And so we have, for example, Pascal dataset, Sun dataset, Coltec, ImageNet, and so on and so forth. Now, this is a sampling of cars or images of cars in the real world, which is much, much larger, of course. But it's a sample. So what they did was the following. They took these 2, 4, 6 data sets. They trained a very good classifier on one data set, and they tested it on the others. Now, keep in mind that this is not, maybe you're familiar with transfer learning, which means I learn a task, and then I transfer my knowledge to another task, which is different. Here we are solving the same problem, detecting a car in an image. The only difference is that here I train it on on Sun 09, and I test it on another data set. Now, these are the figures that they got, of course, in terms of accuracy. You see, of course, on the main diagonal, you will get the best possible values because it means training on one data set and testing on the other. Of course, they use cross-validation, etc. It's not just. But you see what happened when we consider the other data sets. A clear drop in the performance, a substantial drop in the performance. Here you see the difference. On the same data set, 28.2, 19.8%. Drop, 30%. And so on and so forth. On the average, you get these numbers, which is amazing because we are solving the same problem. So we are not changing the problem. And they did the same experiment with person identification. Given an image, tell me whether there is a person. Same story, nothing changes. A person drop on average of about 47, 48%. So this means that data sets are very, very biased, right? And so this is a problem. There is a tendency to think, well, okay, but we can get bigger and bigger data sets, and this is what's going on in the past few years. But I'm not sure this is the right answer. For example, a simple calculation, just a hypothetical calculation done by Theopavlidis a few years ago, shows that the number of meaningful images, it's enormous, 10 to the power of 400. So even if your data set contains 10 millions of pictures, it's nothing compared to the real world. And another estimate gives 10 to the power of 25. So it's impossible to do a good sampling, okay? And so I love thinking that probably when we think that we are solving a problem by using a large data set, large quoted unquoted, we are victims of what psychologists call the belief in the law of small numbers. These two gentlemen are two psychologists, Amos Tversky, who died, and Daniel Kahneman, who got the Nobel Prize in economics. And they did a lot of studies, and they showed subjectively that people usually think that there is a kind of law of small numbers at work, which says basically that random sampling appears to satisfy the law of small numbers, which asserts that the law of large numbers applies to small numbers as well. It's kind of a cognitive illusion. It's not a visual illusion, it's a kind of cognitive illusion. I don't know whether this is an answer to the question why people think that data sets are good and that by getting bigger and bigger data sets we're going to find the solution of our problems. And going back to the problem of bias, well, bias are in humans as well, of course. And of course, it's no point that machines are bias-free, right? Here are some examples of bias, visual bias. We already encountered this one. And in this very enjoyable book, you will find a lot of examples on cognitive biases. So one question is, well, you're building an artificial intelligence, a machine which is should try and mimic the behavior of humans. Humans are biased, so why are you asking for unbiased machines? Let me conclude with a very interesting example of the risks of relying solely on data sets. Now, let's go back to deep learning, this huge neural network with tens of layers and billions of parameters. As I mentioned before, there is this huge data set concerning image classification tasks. These are all labeled, so you get an image and you get a label. There is a car, there is a person, there is a cat, there is a dog, and so on and so forth. Now, a couple of years ago, a breakthrough was achieved. It went on the news. You see, these are some excerpts from newspapers. Microsoft and Google beat humans at image recognition. And the story was basically this. We are seeing artificial intelligence which is getting stronger and stronger algorithms. For example, artificial intelligence was able to beat the world champion in chess playing. Now with Go, you have heard about Go. A lot of problems are being solved by artificial intelligence. Now it's the turn of image recognition. What was the point behind this? Well, basically, it has been estimated that humans have a percentage of error, makes a percentage of error on this image data set of about, I don't know whether, 5.1. Here you go, human benchmark 5.1. So the level of human performance is 5.1%. And deep networks were able to get to 4.94. That was a big breakthrough, according to these journalists, and according to Microsoft and Google, of course. And they claimed we have solved the image recognition problem. We are doing better than humans. Yeah.
Yeah, I mean, the title here is a bit speculative, I guess.
Of course. I know, as is often the case.
This 5.1 actually is Andrei Karpov.
One person. Yeah, I know. I know. But this is the things that you can read in newspapers.
He trained in the weekend and he...
Yeah, I mean, exactly. Yeah, that's 5.1 is one person performance. So not really. Another story is when DeepMind beats, or maybe Watson or whatever, DeepMind beats a player in AlphaGo. There is no percentage there. But I will go back to that story later on. Now, did we already solve the image recognition problem? The answer, of course, is not. Let me just give you some examples. So this is the basic principle behind any machine learning algorithm, which is, we might call the smoothness assumption. Your objects typically are represented as points in some high-dimensional space. These points they get a label, a class, or a color, like in this case. And the principle is points close to each other are more likely to share the same label. So if I give you a new object, a new point or whatever, and this point is here, then I will give it a blue label because it's closer. That's the basic principle. All machine learning algorithms, directly or indirectly, uses this principle. Now, so we have to expect a kind of robustness of our algorithm. By just moving a little bit this point, we should get the same result. So let's see what happens with deep networks. This is an image taken from ImageNet, this huge data set that I mentioned before. If you feed the best neural network with this image, the network will give you the right answer, school bus. Okay? Then we take this image over here, and we expect that if we feed the network with that image, we will get the same answer, school bus. This is wrong. This is the way in which this image has been constructed by just adding some noise. And that's the response of deep neural networks. So it takes as input a school bus, and it says this is an ostrich, which is crazy, right? And what was done here? I mean, what happened was to take the original image, to perturb it a little bit in a proper way. This is not random noise. It's not just random noise. This is important. This is called adversarial noise. Noise that has been created on purpose to fool the network. But then we get something which is perceptually similar to this one. So it's just crazy to think that the network provides us with the ostrich response, right? So this says something very intriguing about neural networks. And you can imagine how dangerous this is if you implement this network in your new self-driving car. Your self-driving car has a camera, and then it takes pictures of the external world, and then he has to recognize road signs because he has to stop at the stop sign. This picture feeds a deep neural network, and then it says stop, and the machine stops. Okay, but then what happens is that this is the input. You change the image a little bit, as I did before, you get this, which is indistinguishable with this one, and the result is yield. And so now you can imagine what happens to the driver, right? So this says something very strong about the robustness of these models, although, as I said before, people claim that deep neural networks are solving all our problems and even beat human performance or human labor. This is interesting, very, very new experiment, very new paper, just appeared a few months ago. This group at Carnegie Mellon invented a system which works as follows. Let's talk about face recognition. So, for example, it could be useful as a biometric system if I have to enter my house or my office, right? So I take a picture of me, and then the system allows me to enter. But if I wear these eyeglasses, the system recognizes this person as this lady over here, which again looks crazy as far as we are concerned, right? And the reason is that these glasses, you see, they are colored in such a way that they fool the neural network. By just wearing your glasses, you just fool your deep neural network. Again, this is not a random noise. It's not, we cannot call it noise. It's a perturbation of the original image, a smart perturbation of the original image. But still, the results are crazy. So let's go back, and I'm almost done. Oops. Now, let's go back to this notion of scientificity. Should we make machine learning a scientific domain or whatever? Well, one of the key things about science is that we have to measure the things that we are working on. For example, the performance of our algorithms. But let's keep in mind that the idea of measuring our concept comes basically from physics. For example, in biology or in chemistry, we don't have exactly the same notion. You don't use integrals or derivatives, or you don't use mathematics at the same level in biology, for example, or in chemistry. So this comes basically from this idea, this, I would say, this obsession towards measurement, comes from the fact that that was proved to be a very successful strategy as far as physics is concerned, but does not translate necessarily to all other fields, as, for example, biology or genetics or whatever shows. So maybe we have to be more careful when we say that a field is scientific, as Lord Kelvin said, when we have a way to measure our thing. This reminds me of the old discussion concerning the intelligent quotient, right? IQ. For example, let's take this sentence from Alfred Binet, a very famous psychologist, the one who invented the intelligence test. At the end of the 19th century, he said that the relationship between the intelligence of subjects and the volume of their head is very real and has been confirmed by all methodical investigators without exception. So he's relating the intelligence of a person with the volume of your head. All these works, as these works include observation on several hundred subjects, we are not in the big data era, we conclude that in the preceding proposition must be considered as incontestable. And here lies the idea that we can measure intelligence with a single number, basically, IQ. And of course, all of you know about the problems associated with IQ. Well, maybe IQ measures something, but is one aspect of intelligence. But indeed, intelligence is it's a variegated concept. And maybe what we are doing in machine learning by insisting on measuring the performance of an algorithm with a single number, the accuracy, the F measure, precision recall, or whatever, it's just more or less related to IQ. So, well, what could be another way of testing our algorithms if we don't have to use any measurement? Well, one example comes from research work done at Johns Hopkins by two well-known researchers, actually four well-known researchers in computer vision, brothers Gieman and Laurent Young. But they justly proposed the use of a visual Turing test. A Turing test, if you might remember, is a test to check whether a machine is intelligent. How does it work? By just asking questions to the machine. The machine tries to make you believe that the machine is a human. And if you get fooled, you will respond that the machine is a human or is intelligent. So maybe we can test our machine learning algorithms or computer vision algorithms using a form of a Turing test. For example, by asking questions. I give you an image or a video and you ask question, is there a person in the blue region? Yes. Is there a unique person in the blue region? And so on and so forth. After a while, this is what we do if we want to test whether the person I'm talking with at the moment is blind or not, maybe, or is not, it doesn't see well. I keep asking questions and I see whether he responds or not. So that could be the next frontier, maybe in computer vision and machine learning. Not just basing our performances on measurements, on numbers, single numbers, but maybe creating a dialogue between us and the system. Okay, so let me conclude very quickly. What I did in these two lectures was basically, besides relating notions well known in the philosophy of science and in machine learning, I also wanted to raise questions. That was my main objective. I don't have an answer to all these questions, of course. So let me just conclude by quoting Jakob Bronowski, a great polymath. He was a mathematician, but he also did very interesting things in the humanities. That is the essence of science. Ask an impertinent question, and you are on the way to the pertinent answer. Okay, so thank you very much. Ask impertinent questions. Thank you for the attention. Questions? Impertinent questions? You will say that deep learning is great. I know that. You know that.
No, I was thinking about this complexity versus interpretability. I mean,
the what? The
complexity versus interpretability.
Oh, the complexity of the model.
I mean, neural nets and random forest and RGM, they are not interpretable. Who says otherwise is lying? But does this claim that regression, for example, is interpretable?
What?
But linear regression, for example, is interpretable.
This has been questioned as well.
I mean, most statisticians say that, yeah, you can interpret it. My point is that if you have a few variables, then yes, you can interpret regression without problem. But in most real problems, you will first have a lot of variables. Then you will look at the combination of them, like put them to the square or cube or whatever. Then maybe do some PCA because now you have too much variables. Then add regularization, and then it might work then. Maybe not as well as neural net, but still it's not interpretable anymore.
I agree. I mean, indeed, if you remember, here in this very room in December, we had the human workshop, and Zachary Lipton was here. He was basically saying that even if we think that linear regression or linear models are more interpretable, well, we have to be careful about this. That's the reason why many things that we have to use natural language maybe instead of this. But this is very difficult, of course. Yeah. More questions?